Hi, my name is Ajay. This is Lab 4 for Physics 1, Modern. So the purpose of this lab is to compare the predicted motion with the observed motion of a mass oscillating from a spring in the both x and y direction, and the mass is hanging down from the spring. Um, so we're going to plot the change in energy to look at how the energy principle acts in this scenario, and we have kinetic energy, gravitational, spring potential, and then obviously total energy. But we'll talk more why we have those kind of energies when we get to system and surroundings. Group concepts covered. We're going to cover Newton's second law, spring force, energy principle, and the result of the lab. Our predicted model was actually very similar to the observed model from the video, and then our change in energy is zero, affected by the energy graphs due to the conservation of energy. Um, so some concepts we're going to cover. We're going to use position update as well as velocity update, and then kind of the main concept we're covering is Newton's second law, which for this experiment we're going to use the formula F net is equal to change in momentum over change in time. And then we have our energies on the right: kinetic, gravitational, and spring potential. Um, so for this experiment, the system and surroundings. The system will be the Earth, the spring, and the mass. And this goes back to the energies of the system. We have kinetic for the actual movement, and then gravitational potential from the Earth, and spring potential from the spring. Since um, our mass is not the entirety of the system, we have those other energies. And in this case, we have no surroundings because everything is part of the system. So our energy of the system is equal to the kinetic plus the potential, gravitational, and the spring potential energy. Um, Also, it's at rest to start with, and then we have a position um, that we start with listed. And then here's the actual movement. Okay, so it moves in an oscillating motion both in the x and y direction. That is important for later. So here's the code, some initial conditions, and computating the energies. Um, Here's some more, the rest of the code. So then here's some graphs. So this really quick video is the simulation of what the oscillation, which looks very similar to what we tracked using Tracker. And here is a energy graph on the right, totaling all the energies. This is important for one of our later questions. So let's talk about sources of error real quick. Drag force, there will be air resistance in real life. It might be small, but it will still be significant in terms of it being a closed system or not. Tracker issues might have misclicked and not accurately clicked on the center of mass for it, uh, the mass that was oscillating, and as well as we might have an imperfect spring. Springs can be bent and lose their perfect spring capacity and stuff like that. So that's something we need to consider. And then also an imperfect release, if like instead of just dropping something, you push it a little bit, it might affect the motion a little bit. Because we are recording in 2D, um, we do not get the third dimensional aspect, so it might be a little bit different than what it should be, like in theory. So back to this energy graph. Is the energy principle satisfied in this experiment? Yes, it is. So delta E, which is the orange line in this graph, is zero the entire time. So at any given moment, all of the energies will sum up to be zero, but the type of energy changes throughout the experiment, as we can see on this graph. As stuff goes up and down and the spring releases, we get to see different changes in energy. And then our second part of discussion, um, estimate the period of oscillation from the data. So we calculated the x oscillation to be 1.7 seconds and the y oscillation to be 1.5 seconds. Um, they should be closer to about the same time, and that would kind of give us a more circular oscillation pattern. If they were exactly equal times, which that comes down to air. Um, but these stay consistent pretty much throughout the entire experiment.